Hello friends, I am Dr. Archana Chaube, Faculty of Science, the Bhopal School of Social Science. Today I am here to discuss an important topic from electrochemistry, that is Kohlrausch law of independent migration of ions. In this lecture, we will be discussing the following topics: electrolytes and types of electrolytes, conductance, under which we will see specific conductance, equivalent conductance and molar conductance. Then factors affecting electrolytic conductance, effect of dilution and Kohlrausch law and its applications. What are electrolytes? Electrolytes are substances whose aqueous solution allow the electric current to pass through them. The ions which are present in these substances are responsible for the conducting movement. Examples of which are salts, acids and bases. So, we may say that ionic compounds are substances which form electrolytic solution when dissolved in water, whereas substances whose aqueous solution do not conduct electric current are called non-electrolytes. Example, sugar solution. Now, we have seen what are electrolytes. If we see the classification of electrolytes, electrolytes are of two types: strong electrolytes and weak electrolytes. This classification is done on the basis of the ability of the electrolytes to get ionized. The substances which are called strong electrolytes are those which are highly ionized in solutions in all concentrations. The examples of which are HCl, NaOH, CH3COONA, H2SO4, HNO3 and so on. Similarly, weak electrolytes are substances that are feebly ionized in solution, or we may say they are very less ionized in solution. Examples: ammonium hydroxide, acetic acid, etc. Now, when we are talking about electrolytes, there are certain important terms we must know. There comes the property of conduction, and so we must know what is conductance and resistance. First, we will see what is resistance. Resistance is actually a frictional force, or we may say resistance refers to obstruction of flow of current. It is a property of the substance that does not allow the current to flow through it easily. So, if we take an example of a conductor of length L, this is the length, and the cross-sectional area is represented by small a, then resistance capital R is given by its relation that R is directly proportional to length and it is inversely proportional to cross-sectional area. Combining the two relations, we can say that R is proportional to L by A, and removing this proportionality sign with an equality sign and putting in constant rho, we get the formula R is equal to rho L by A, where rho is the constant of resistivity, or it is known as specific resistance. By this we know that if the length of the conductor will increase, the resistance will increase, or if the cross-sectional area will increase, the resistance will decrease. Next, the another property is conductance. since resistance is a frictional force which inhibits the flow of current, so conductance is just an inverse property of resistance and it is denoted by capital C. We may say that it is the reciprocal of resistance and its formula can be given as C is equal to 1 by R. So, the substances which easily allow current to flow through them are called as good conductors. The units of conductance are ohm inverse, mhos, or SI unit is Siemen. Now, conductance is of broadly three types. First is specific conductance. As the name suggests, specific conductance, it is defined as the conductance of a unit volume of a cell. That means if we take this 1 centimeter cubic cell, so the number of ions which are present in this cubic cell, these ions will be responsible for the conductance which will be measured, and this conductance is known as specific conductance. Specific conductance is given by letter K and it is the reciprocal of resistivity. Just now we had seen the formula of resistivity rho. We had seen R is equal to rho L by A, from which we have derived the formula for rho, that is equal to cross-sectional area into resistance upon length. Therefore, we may say that specific conductance is just the reciprocal of this formula, which is L upon A R, where the quantity L by A is termed as cell constant. The units of specific conductance are ohm inverse, centimeter inverse, and its SI unit is Siemen inverse. The second property is equivalent conductance. As we had seen, specific conductance is specified to a unit volume, whereas equivalent conductance is the conductance due to the ions which are present in the total volume of the liquid. Or we may say it is the conductance of all the ions furnished when 1 gram equivalent of an electrolyte is dissolved in V centimeter cube of a solution. That means we can say that if this is a beaker and it has 100 ml of liquid, so all the ions which are present in this beaker, all the ions, the conductivity will be responsible in total will be given as equivalent conductance. It is denoted by lambda subscript equivalent, and it can be mathematically written as K into volume or K into 1000 upon normality, where K is the specific conductance and V is the volume of the solution when 1 gram equivalent weight is dissolved in 1000 ml of solution. So we are talking in terms of normality. Now, if instead of normality we take molar solution, then the conductance will be called as molar conductance. What is molar conductance? It is the same as equivalent conductance, but just the difference is that in equivalent conductance we talk about normal solutions, whereas in molar conductance we talk about molar solutions. It is also represented by lambda subscript small m. So we have discussed about the three types of conductance: specific conductance, equivalent conductance and molar conductance. Now, what are the factors which affect this property of conductance? First is the nature of electrolytes. As we have seen, electrolytes are of two types: strong and weak. So, the strong electrolytes are those which ionize very easily and completely. Therefore, strong electrolytes will ionize completely in the solution and they will be good conductors, whereas weak electrolytes are feebly ionized, or we can say they ionize to a small extent, so they are not so good in producing electrolytic conductance. Second property is size of ions. Larger the size of the ions, smaller will be the conductance. Third is nature of solvent and viscosity. When we talk about the nature of solvent, we talk about the polar and the non-polar substances. So if the solvent is highly polar, the highly polar solvents will increase the conductance of the electrolyte, whereas less polar solvents will decrease it. Similarly, if we talk about viscosity of the medium, the viscosity of the solvent, if it is higher, the conductance of the solution will be lower. So we may say that polar solutions will increase the conductance, and with increase in viscosity, the conductance will decrease. Moving further, the next factor is concentration of solution. So, higher the concentration of the solution, less will be the conductance, which means that concentrated solutions have more ions and they have less space to move. Therefore, their conductance is less. As we dilute the solution, the volume of the solution will increase and thus conductance will also increase. Next factor is temperature. As we know that temperature is a source of energy for any molecule, so with increase in temperature, the dissociation of electrolytes will increase. With increase in temperature, the dissociation will also increase and thus the conductance will also increase in the solution. Now, as we have just now discussed that concentrated solutions have less conductance and dilute solutions have more conductance. So, what is this effect of dilution on the conductance? We may see that among the three conductants, specific conductance will decrease on dilution because the number of ions present in a cubic volume will decrease on dilution, whereas equivalent conductance and molar conductance are the properties which will show a rapid increase on dilution. Also, if we compare the effect of dilution on weak and strong electrolytes, we may say the effect of dilution is seen more prominent in case of weak electrolytes than in comparison to strong electrolytes. So, this effect of this difference of behavior of weak electrolytes and strong electrolyte on dilution was studied by Kohlrausch, and thus he gave the Kohlrausch law of independent migration of ions. This law can be stated as follows. At infinite dilution, where all electrolytes are completely dissociated and where all interionic attraction disappears, each ion migrates independently, unaffected by the nature of its co-ions, and it contributes a definite share towards the total equivalent conductance of the electrolyte. By this we mean that on reaching the infinite dilution, when we measure the equivalent conductance of an electrolyte, at this place the ions in the electrolyte are far apart and they are moving independently and are not affected by the neighboring ions which are present in the solution. And in this condition, each ion gives its specific contribution towards the conductivity of the total electrolyte. It can also be stated as, at time of infinite dilution, the molar conductance of the electrolyte is expressed as the sum of contribution of the individual ions, which can be represented as lambda m or lambda equivalent for both at infinite dilution is equal to V plus lambda infinity plus V minus lambda infinity minus, where V plus and V minus, they represent the number of the cations and the anions, and lambda plus infinity and lambda minus infinity, they represent the ionic conductance of cations and anions respectively at infinite dilution, whereas lambda equivalent with infinity represent equivalent conductance at infinite dilution. So we may say an example like the molar conductance of HCl at infinite dilution is given by the sum of the equivalent conductance of hydrogen ions at infinite dilution and chloride ions at infinite dilution. This is basically the Kohlrausch law. Now let us see the application of this law. Kohlrausch law helps us to determine the equivalent conductance or molar conductance at infinite dilution for weak electrolytes. This law is basically developed to explain the behavior of weak electrolytes, because the equivalent conductance of strong electrolytes can be graphically calculated, whereas that of weak electrolytes, it is impossible to calculate the equivalent conductance. So we have to use the Kohlrausch equation. Now let us take the example of sodium acetate. When it reacts with HCl, it gives acetic acid and NaCl. If we want to calculate the equivalent conductance of the weak acid, acetic acid, we will use the 3 strong electrolytes to calculate its value. Here we can see the ionic composition of the 4 electrolytes. Acetic acid is made up of CH3COO minus H plus. Sodium acetate is made up of CH3COO minus Na plus. HCl is made up of H plus and Cl minus, and NaCl is made up of Na plus and Cl minus. Let's see. The equivalent conductance at infinite dilution for the weak electrolyte, that is acetic acid, can be calculated by adding here we are adding the ionic conductance of sodium acetate and HCl. By this we will subtract the ionic conductance of NaCl at infinite dilution, and on solving this equation we will get the result for the weak electrolyte, that is acetic acid. When we open the bracket, the equation will be the sign will change and we will see that the like terms in the equation will get cancelled, resulting into our final equation where the equivalent conductance for acetic acid will be obtained. Since the sodium ions as well as the chloride ions being common with the opposite sign will get cancelled, resulting in the formation of acetate ion and hydrogen ion, which are our desired product. So by this equation, we can say that to calculate the equivalent conductance at infinite dilution for CH3COOH, we have to simply add the equivalent conductance of CH3COONA plus HCl, and from this we will subtract the equivalent conductance of NaCl. Friends, I hope all your queries regarding this topic must be cleared. Thank you.